Good morning, my lovely pre-cal students. Today we're going over 10.5, where we get to take our vectors and apply them to real life. This is a really cool lesson. There's a lot of story problems, lots of real-world relevance. So let's get right into it. So you should remember from our last lesson yesterday that a vector formed by the addition of two or more vectors is called the resultant. That vectors have both magnitude and direction, and that vectors follow the rules for scalar operations on page 659 in your textbook, which you should have written in your notes. So the new material today, the first is about unit vectors. Unit vectors have a length of 1. They will still have a direction, and the direction of a unit vector will relate to the vector it came from. So remember that the double lines on either side of a vector mean that it's the norm, which is very similar to the modulus, or r. Okay? Unit vectors are found by multiplying a vector by the reciprocal of its norm. We'll go over a problem like that later. So now, the really cool thing today is alternate vector notation, or linear combination. So if we take the unit vectors I is equal to 1, 0 and j is equal to 0, 1, we can then rewrite a vector, like let's say u is equal to 5, negative 7, as 5, 0, 0, negative 7. We apply each of the unit vectors to it, and bada bing, bada boom, look, we have your nightmare, the complex number. Okay, well, it's going to be fine because we've done complex numbers before. This is essentially going to be going back to 10.3, where we're finding the modulus and theta, except this time we're calling it the magnitude and direction of the vector. So we use the same formula for the magnitude, square root of a squared plus b squared. Furthermore, we have a little bit of a shortcut today. To find the direction of a vector, you take the inverse tangent of b over a. We do this, as we saw in the last section, because the sine of theta is equal to b over the norm, or modulus. The cosine of theta is equal to a over the modulus, or norm. And by the quotient identity of tangent, sine of theta over the cosine of theta. Okay? So our first problem is very simple, just showing that this special new form called linear combination. It deals just like the vectors that we did in the last section. So whenever you're performing scalar operations, just remember to keep like terms separate. Keep your i's together and keep your j's together. I's and j's do not mix, people. All right? So we have I minus j minus 2i plus j. We just do simple addition and subtraction. Bada bing, bada boom, we're done. Okay. This next one, we're finding the component given the magnitude and direction. Component form is where we have our a and b with the carets on either side. So this question is asking us to find a and b. We use that by taking advantage of our trigonometric ratio. Sine of theta is equal to b over the norm. Cosine of theta is equal to a over the norm. We solve for a and b, and we end up with the component form. Question 23, we're doing the exact opposite. We're given component form, and we find the magnitude and direction. Remember, magnitude, or the norm, is equal to the square root of a squared plus b squared. We plug in a and b, get our answer. Direction, remember, it's equal to the tangent inverse of b over a. We plug in our numbers, take the tangent inverse, and we got our direction. For these problems, if they're asking for degrees, make sure your calculator's in degrees. If they're asking for radians, make sure your calculator's in radians. Okay, finding the unit vector, very easy. We just find the norm, and then we multiply our vector by 1 over the norm, which is the reciprocal of the magnitude. Right here we find that our norm is the square root of 41. So we just multiply our vector 4, negative 5 by the 1 over the square root of 41. And we're going to convert it to this linear combination form whenever we do that unit vector. So it'll be 4 over the square root of 41i plus negative 5 over the square root of 41j. So now on to more real-world problems. These are multi-step problems. If you want to Zoom me to go over them one at a time, that's great. I'm going to go over a more bland one, then we're going to go over an airplane one. There are other examples in your book, like the inclined plane pulling a wagon, elephants pulling a cart, that kind of thing. If you would like to go over those in person, I'd love to. I'm doing one for the sake of board space and time. Okay? They're all going to have these basic steps, 4 basic steps. First, we rewrite the vectors in linear combination. We perform the operations to convert to component form. What that means, I have the 12, the cosine of 130. So I take the cosine of 130, multiply it by 12, and that's my A. I have the sine of 130. I multiply that by 12, that gives me my B. Okay? It's just doing this operation, there we are, over again. So we're solving for A and B instead of theta. Okay? That's why it works that way. Anyway. For 34, we're starting with 12 at 130, 20 at 250. We rewrite it. You can see it there. Now I put those into the calculator and I get these vectors. The resultant is the addition of the 2 vectors, so we just add them together. Simple. Then we find the magnitude and direction. A squared, B squared, inverse tangent, B over A. Very simple. You guys got this. They look difficult. All the steps are easy. We've done them before. Okay? Now, this problem, the airplane problems, are a little bit more complicated because they're written in a confusing manner. So when it says course, that's going to be your theta or your direction. Ground speed is going to be your magnitude, okay? They're going to give you an airspeed and a wind speed. We're mostly going to follow the same steps as number 34. However, they were very, very tricky when they gave us those angles. If you notice and remember, in navigation, we go in angles in the clockwise direction. Whereas in math, we do the counterclockwise method. So the first thing that we're going to have to do is convert these angles from clockwise to counterclockwise. The first one is very easy. We'll go 60. So in counterclockwise, starting at the x-axis, it goes up 30 degrees. We're done. Okay? The next one's a little bit more complicated. Remember, it says the wind is blowing in question 42, which means that it's actually going to be moving in the opposite direction. You can see I've drawn a line showing the wind moving. It said it's blowing from 120 degrees, which means it's blowing to negative 60 degrees. Draw a line. It'll help you a lot for these problems. I would definitely practice the airplane problems for the test. Anyway, after we've done that hard work, we just need to define our vectors, rewrite them, find their component forms, add the component forms, then find the magnitude and direction. Fairly simple after that. Like the other story problems from this section, it's just a conceptual problem of understanding what's going on. The math is not difficult. Anyway, I love you guys. Thank you so much for your communication. Please let me know if you have any questions from the homework on 10.5. If not, I will see you tomorrow.